This is the story of the one. As head of maintenance at a concert hall, he knows the show must always go on. That's why he works behind the scenes, ensuring every light is working, the HVAC is humming, and his facility shines. With Grainger's supplies and solutions for every challenge he faces, plus 24/7 customer support, his venue never misses a beat. Call quickgrainger.com or just stop by. Grainger, for the ones who get it done.
For the ones who know safety isn't a catchphrase, it's a culture. And the ones who help make sure everyone makes it home safe. For the safety-minded who watch everyone's backs, Grainger offers supplies and solutions for every industry, as well as safety assessments and training to keep your facilities safe and your people safer. Call, clickgrainger.com, or just stop by. Grainger, for the ones who get it done.
Physical objects are everywhere, and they're all made out of molecules and atoms. However, the arrangement and refinement of these atoms can be the difference between a computer and sand, or between a tree and paper. For a species as reliant on tool use, the ability to conceive of, design, create, and produce these materials is an ongoing concern. Since we've been around as humans, and even before, we've been material scientists in some regard, searching for new materials to make things out of, including the tools we use to make things. So what is the difference between iron and steel? How do we think up new things to make things out of? And what are time crystals? All of this and more on this episode of Breaking Math. Episode 74, Materialism. I'm Sofía.
And I'm Gabriel.
And this is Breaking Math. Well, with us, we have on Taylor Sparks. Taylor, how are you doing?
I am so great. It's a pleasure to meet you both.
Pleasure to meet you as well, sir. I think we were first acquainted on Twitter a while back, weren't we?
I honestly, at this point, I don't even remember.
Oh, I do remember. There was a Reddit thread about recommended science podcasts. And we are currently talking with some public schools about what would be some great podcasts for their kids. And in the science category, you guys came up among a whole bunch of them in biology and some other ones as well as some TikToks. And I was like, materialism, interesting, because our listeners may or may not know this, but although I'm an electrical engineer by trade, I actually wanted to be a material scientist for many, many years, inspired by Richard Feynman. And if you wouldn't mind, what's that Feynman quote that you all know?
Yeah, so at the beginning of our episode, we actually have this music we had made, and it starts with a quote from him called "Plenty of Room at the Bottom." It's one of these classic quotes where he essentially kicked off an entire field of the miniaturization of materials. It's called "Plenty of Room at the Bottom," basically suggesting we can make things smaller, not just like a little bit smaller, like way, way smaller, like Honey, I Shrunk the Kids smaller, and make amazing devices if we can pull that off. And it really did. It's kicked off a whole, revolution in wild material science.
Yeah, I've read that Feynman paper where he talks about the robot that can make a robot like 90% of its own size. Basically he's saying like, yeah, if you do it like 90% over and over again, you could eventually end up with nanobots if you can make a self-replicating machine.
You know, it's crazy. When he put this challenge out there with his talk, he said, I'll give it, I don't remember what the prize was, like $1,000. It wasn't very much, but he was like, I'm going to give this prize for the person that can write a page of a book on the head of a pin. And the first person who technically did it was a watchmaker, right? Because these watchmakers have these tiny little intricate tools that can like do it. And so technically it qualified, but it was like cheesy. So he gave them the prize, but it was cheesy. The first person who actually did it was a graduate student, and they harnessed an electron microscope. So you take this beam of electrons and they were able to write A Tale of Two Cities on the head of a pin. And that was really like the proof of concept that people needed, like, holy smokes. You can do it. You can go way smaller.
Like the whole book then on the head of a pin, or?
Just the first page or two. Okay. But I mean, you could, right? Because it was tiny. And nowadays you totally could actually, because we can write incredibly small things we can write the nanometer level. So yeah, you could write the whole book if you wanted to.
Wow. Cool. So before we go further, I think we're going to just ask you a few questions about who you are, what's your show, etc. So who are you? What's your show? Where do you hail from, etc.?
Cool. Yeah. So I'm Taylor Sparks. I'm at the University of Utah in the Material Science and Engineering department. And if you were like me and you've never even heard of material science, it's in the College of Engineering. It's probably the smallest of the engineering disciplines. You've all heard of electrical, mechanical, civil. Materials is there, though. Not every school has it. It's one of the youngest disciplines. It really showed up in like the 50s. And so computer science is newer, but it's relatively new. Yeah, I'm a professor at the University of Utah. It is a phenomenal department. We're small, but we do lots of great things, from polymers to metals to ceramics. Like if it's a material, whether it's a biological or a hard or whatever material, there's folks in our department working on it. And I started the Materialism podcast with one of my undergraduates actually 3 years ago, because I was just tired of nobody knowing what we were and what we do. And so I wanted to get the word out. And At the time, podcasts were sort of an emerging medium that everyone I was talking to was listening to them. And I was bugged because there was no good material science podcast. The ones out there were these dry, boring interviews with people who weren't really good at talking about their work. They just sort of yammered on. So we have tried to turn that on its head with our Materialism podcast by making it very, very, very accessible.
Oh, that's really exciting. Let me tell you why I'm excited right now, actually. Because with this time where podcasting is a thing, it's possible to get really passionate people to talk about a subject and build a network. And in my imagination here, one of our listeners may not know what they want to do with their life when they'll hear something about material science or on this podcast and think, oh, that's a cool area. I could research that. So you mentioned that materials science and materials engineering is a smaller discipline. I was surprised when I discovered that as well. I'm an electrical engineer because when I looked at the job postings at our local labs, the engineers, there were so many more electrical engineers at the time than there were materials scientists, just as a full disclosure. But that said, Feynman said that quote, over 50 years ago. So one of the questions I might ask you is, I know that it's a smaller community, so we can talk about some really cool stuff and have some cool, networking. But why is it smaller? And in your view, is the field growing or is it steady or what? What's the state of the field?
Great question. Why is it small? Maybe a couple reasons. People just sort of assume there's this presumption that the right material is just there, right? If you just look hard enough, you'll find it. You can head over to Home Depot and get that exact grade of whatever aluminum or alloy or whatever you're looking for. And it's only later on that you realize well, shoot, actually it doesn't exist yet. It's not available, right? And so there's this assumption of just the materials are already developed for us. But I think that later on in your career, you start to realize that actually you do need to make those things. So that's I think one reason why there's fewer positions is people don't think that it's necessary until it is. And then the second reason is that a lot of our graduates are in competing fields as well, right? Chemical engineers, mechanical engineers, physics, chemistry. All of these people are largely studying materials problems. Not entirely, but there's a big fraction of those disciplines that are doing materials research. And so it's sort of become broadly dispersed across the other engineering disciplines.
That was actually going to be my next kind of question, the world's made out of material, right? So it's kind of surprising that it's such a small field. I guess what I'm going to ask is what's the difference between a material scientist and, for example, a weaver or a blacksmith or a metallurgist or...
Oh, that's a great question. So at its heart, some of these more artisan disciplines who are doing materials, they're making materials. I'd say the biggest difference is understanding we call it the structure, property, processing relationships, right? We know mechanistically, from what's going on at the atoms or the crystal structure or at the grain level, we know why when you make a material a different way, like when the blacksmith quenches it in oil versus water. The blacksmith knows that one gives you a hard material and one gives you a more ductile material, but they couldn't tell you why. Material science investigates the why, the mechanistic relationship between those sort of processing, structure, properties, performance, linkages. That's, I think, the biggest difference. But those people make materials, and they make great materials. They just don't always know exactly why.
And so you say in the structure, I'm guessing that you're talking also about structure that isn't just bonds, right? You're talking about the shapes and stuff, because it seems like that's the biggest difference between material science and chemistry, for example.
Yeah, I would say that is a major difference between materials and, say, chemists or other fields, is that we do take into account structure beyond bonding. In fact, we zoom out, we talk about crystal structure, where now it might be lattice motifs. Maybe you've got a little octahedra, this little sort of shape that could be connected in different ways. If it's connected along the corners versus the edges versus the faces, you get totally different properties. So that's part of it. But you could zoom out even further and you could say if you looked at something under the microscope, you can see the little, what we call grains, regions of where the lattice is sort of aligned with one another. Imagine if you're tiling a wall. So Sofía, if you started tiling the wall on one side of the room with some orientation and Gabe was on the other side of the room and he started to tile that wall, eventually you're going to run into each other and those orientations might not match. So we call that a grain boundary, separating two grains where the orientation is just mismatched. So that's an important part of structure. And then you can zoom out even further at the device or the component level, sort of in the mechanical engineering domain, where you say where the struts are, where's the porosity at, how do things get joined? All of those things are all structure. None of those is not structure, and they all impact properties differently.
That's really cool. And the last question we're going to ask you before we sort of dive in is, why did you get interested in it?
Oh, okay. So yeah, I always liked engineering and science and tech, and I was just one of these people who couldn't pick, right? It all sounded cool. I wanted to be a manufacturer of robots. I wanted to work in aerospace. I wanted to do all the things, and I didn't like having to pick because then you're stuck. And so when I was talking to counselors, I did a year of college to sort of knock out some calculus and chemistry generals, and then it got serious where it's like, there's no more generals left to take. You've got to get into your discipline. So I started talking to advisors, and I met with this gal, Ashley, who, changed my life because she's like, hey, you don't have to pick. Material science is at the confluence of chemistry, at physics, mechanical engineering. Like, it combines all those disciplines together in this really, really wide discipline where you don't just become like a SolidWorks expert or just like a heating and air conditioning expert. Like you can do all of those things because all of the things in engineering are materials limited. And it's a fun field to be in because you can just jump around from topic to topic as it interests you.
Oh yeah, that's actually the exact reason why I like math and computer science. So what we're going to do, just to give you a quick bird's eye overview, we're going to talk about some how to learn material science, some general kind of like questions about materials, about the evolution, and then finally maybe some fun questions about exotic materials, and then maybe a free range section.
All right, Taylor, so I have a few questions about learning material science in general, about what would be a good base. So I guess I'll ask a few of them at first. So what is important to know in terms of chemistry and physics and perhaps mechanical or electrical engineering?
The short answer is everything, right?
Yes.
Material science studies everything. It's a shallow major and a wide major, as opposed to like a really deep but specific one. So if you study metallurgy, for example, you're going to study all the things about metal, but you could be a super expert in that field, but you won't know anything about polymers, right? Materials is meant to be the complement to some of those deep specific majors by being very broad, but not quite as in depth. We want people to get a broad understanding, knowing that later on in their careers, they'll be able to do the deep dives. So when you say, is it physics, is it chemistry, is it electrical engineering? Our students take all of those courses, right? They take calculus series, they take the PDEs, the ODE series, all the way up to stats typically. So they get a very broad math background. They take the physics 1 and 2, right? So your Newtonian mechanics all the way through electrostatics and dynamics, right? Mechanical engineering, they take statics and kinetics typically. ECE, they take circuits, which some of that they've seen in physics before. They take general chem 1 and 2 plus OChem 1. I mean, it's broad. It's broad. Now, we do allow some technical electives. So if you know, for example, that you want to go into biomaterials, you can start to specialize a bit and take more bioengineering classes or, drug discovery classes or biology classes. But there is a broad base. Like the core courses for this department are incredibly broad.
Nice. That's an area that'll get exciting. Is talking about biomaterials. And as a follow-up to my last question, let's pretend that one of our listeners wants to teach themselves material science. Is there anything that you can recommend in terms of starting YouTubes or a podcast or anything like that?
Well, I'm going to plug my own work for sure. Like, the Materialism podcast is a great place to figure out if you're even kind of interested. I think that you'd like our podcast, right? I think it'd be a great place to learn about some of the fun, sort of entertaining aspects of it. But if you want to get into like the actual content, there's a couple resources. First off, during COVID, when the rest of the world had sort of stopped teaching in person, I was no different. And I, for a few years before that, had been putting content on YouTube. And I really picked it up and got, I think, a lot better on it. So you can check out, just Google Taylor Sparks on YouTube and it'll pull right up. I have a playlist as an introduction to material science playlist. And I've broken the content into like little 5 to 10 minute blurbs instead of hour-long lectures, which I think is maybe more the speed of a lot of people. They want to learn about a little subject instead of a whole hour-long lecture. But anyways, that's a great place to start. If you're not the type of person to watch videos and you'd rather read something, then there's no substituting Bill Callister's Introduction to Material Science book. He's actually from the University of Utah, and yet this is the seminal book used all around the world. Bill Callister wrote this thing, I want to say the 80s or something, and it's on its 10th edition. It's one of these classic books that everyone in the field uses. It's written in a really simple, easy to grasp way. They take a high overview of everything from crystal structures to phase diagrams to processing of materials and everything in between. It's a great resource. And it's easy to read.
The state of Utah is inspiring not only this podcast episode, but our next one as well. It seems that the material scientists, but also a lot of the computer graphics people that we're researching all come out of Utah. So that's kind of interesting.
Yeah, so like John Warnock, the Warnock Engineering Building is where most of our offices are here. Yeah, they have done some amazing things for graphics.
Wow. Interesting.
Kind of like, like when you're learning, painting, it's good to like have like, a thought, like, if you want to do something kind of like, pretty. If you're doing math, you want to do something like, either correct, or if there's different frames of mind that people are in with different subjects. So I was just going to ask you, what frames of minds, concepts, paradigms, factoids, etc., are useful to know or be cognizant of to learn material science better?
Oh, that's a great question. I would say the best frame of mind for materials science is probably a curious one that is observing the problems in the real world, right? Every time that you use the materials all around you, whether it's, electrical tape or duct tape or whatever, like think about the current pain points with using that material. What is it that you just hate about it? And then take that problem with you and start thinking about, why does it have that properties? How could you process it differently? How could you change its chemistry a little bit differently? How could we try and address that problem? That's, I think, where some of the coolest breakthroughs in material science have come from, is people just frustrated with the current fleet of materials and basically said, like, I just want something better. And sometimes that's science fiction, like the classic example is from Star Trek, right? Where they had this whale, what is it? Movie number 4, was it? The Return Home. Anyways, they had this giant whale and they put it in this container with transparent aluminum, right? And at the time that didn't exist. And what would a transparent metal even be? And that sort of was the impetus for a lot of research. And all of a sudden we now have transparent metals, right? Transparent conductors, which I think grew out of this totally crazy, unrealistic science fiction observation of something that could be. That's the attitude to have.
That's amazing. Before this conversation, I was not even aware that transparent metals existed.
Same.
I was aware that there was somebody who treated tree bark and made a transparent material out of tree bark. So this
really?
is, yeah. And I saw that actually when we were first planning this episode back in January. It's been that long.
I know, right?
Yeah. But yes, transparent tree bark. And then you have transparent material. And all of this is just so fascinating.
Well, I know transparent glass. That's one of the things I know about material science, was like a big breakthrough in 14th century, something like that.
My goodness.
50th.
Yeah. And so now imagine, like, if you could take that glass and have it be conducting, or conducting just in certain parts, like you can make wild stuff with it. So think of like a solar cell, right? A solar panel on your roof or wherever you might have one. The sun has to come through, so it has to transmit through the top of that layer, right? So it has to be transparent. But then when it actually creates the electron in the hole that allows to actually be a battery, right? That allows you to harvest power from it. You have to extract that electricity from the top of that panel, which means you have to have a conductor there. So they actually put a very thin, what's called a transparent conducting oxide on the top of every solar panel and on your phone screens, right? This is a glass screen on my phone. And the reason I can get the properties of being able to swipe and tap and do all these things with it is because we have transparent conducting oxides on these things.
Wow. If you don't mind me asking, as you're saying this, one of the things that I'm thinking of is as having a real understanding of the thermodynamics at stages of everything that you're talking about. So I should say not peripherally, but related to that, a question for you. This is all very, very fascinating. As we've said earlier, before this conversation, I didn't know that transparent metal existed. And then the only thing I knew about was a tree bark that was treated in a way that made a transparent wood. And then that reminded me of that Simpsons episode when Homer grabbed the chicken leg and rubbed it on the wall, and it turned the wall transparent. And then the bird flew into it.
I have not seen that one.
Okay, this was like 1994, I think, when that episode aired, something like that. Anyways, this is just fascinating. So here's my next question. Now, this is not meant to be a curveball. This is meant to be like something with a lot of meat on it. There are some incredible discoveries that completely changed the field of materials science. We could talk about metallurgy itself. We could talk about even plastics in the last 100 or 200 years, or we could talk about, anything really. My question for you is, what do you think are some of the biggest discoveries, either accidental or well, I guess just accidental, I suppose, in all of material science that had the biggest impact?
Well, accidental or on purpose, man. And specifically, how can someone use this to be able to learn material science better?
So to answer both your questions, there's a great book. It's called The Substance of Civilization. Let me make sure that's the name. I'm pretty sure that's it. Just give me one second. Yeah. So, great book called The Substance of Civilization by Stephen Sass. This is a fantastic book written in a very super non-technical way. Anybody could read this and get a kick out of it. What I like about it is it takes this historical perspective from caveman all the way forward, and it talks about how these big advances in society, like major advances going from like the Industrial Revolution, right, into like the information age and all this, was really materials dictated. There was a materials breakthrough. And so he starts with like the Stone Age. Like, why did they use stone? Because it was the best material. It was better than wood. It was better than these other things for it. And here's the reasons why. And then all of a sudden you get the appearance of bronze, and holy smoke, somebody figured out that if you take these copper laden minerals and you put it in a hot enough fire, all of a sudden you get this funky metal that comes out, and they could make tools and weapons and all all these different things with bronze. And then iron shows up, and holy smokes, iron has been like incredible. It remains very important, but huge advance over bronze. And that gave way to steel, and steel unlocked wild new things. For the first time, we could build structures in tension, right? Before that, if you look at old buildings, they're always built in compression, hence like the arches that had like the keystone holding it all together. But you could never build a skyscraper with that. You needed things that could withstand tension, meaning pull them apart, and steel unlocked that. You had the birth of semiconductors, right? And electronic devices in the sort of post-World War II era. In fact, only since like holy cow, and like definitely in the last 100 years, every polymer, like every plastic that you see, from PVC to polyethylene to Teflon to polypropylene, synthetic shirts we clothes, everything around us that's plastic was it developed basically in the last 100 years, which is absolutely crazy. PVC was in the 70s, right? That's not that long ago. You ever wonder why these old homes don't have PVC pipes? They have like corroding old gross pipes because it wasn't around yet. This is like so brand new, and yet it has transformed the world around us in such wild ways. LEDs and lasers have unlocked crazy technology. I could go on and on, but there's just been some massive breakthroughs that transform the way we do life, and we're sort of ignorant to it because we know our own experience, right? All we know is what we've sort of seen, and we don't have the luxury of, temporarily existing 100 years ago and seeing that, oh, that's what you guys used for biomedical engineering, right? Was a piece of leather to insert into somebody's body. Like, no wonder you got sick all the time. Like we don't even realize how good we've got it because we benefit from millennia of materials development.
That's horrifying, the leather thing.
Oh yeah.
Dude, catheters used to be leather. They would, pretty wild.
Oh my goodness. That's insane. That's insane. Sorry, my mind is just blown right now. I'm like, my mind is too blown. I have to recollect myself.
Oh yeah.
Well, let me tell you this. Those are some of the things that are just shocking to me. But in preparation for this interview, I did a bit of Googling because I was curious, like, what do people, not just me, but other people generally think are the major breakthroughs in material science? Let me list a couple of these off. So full disclosure, this comes from Materials Today, which is one of the sponsors of our podcast. It's a journal by Elsevier. But it's about 15 years old, so it's not even brand new. But here's 10 things that this guy, Jonathan Wood, one of the editors at Materials Today, listed as sort of the biggest impacts. The first one was the International Technology Roadmap for Semiconductors. So every year, this roadmap gets put out, and it goes 15 years out, and it basically says, like, as a humanity, like, here's the things that we're going to do in the semiconductor space to make, information storage and communication and computing all possible to far better degrees. So that's one of the big things that he lists. He lists the scanning probe microscope. So this came out in the 80s. If that is a bunch of gobbledygook for you, scanning probe microscope. Just imagine a microscope that could look so much like magnified down that you could actually see atoms, where they are, and how they interact at an atomic level. That unlocked crazy possibilities.
I have seen that. Wasn't that the first pictures of atoms that confirmed that chemists were correct about the angles?
Yeah, because before then we had diffraction. Diffraction is about 120 years old. We had Bragg and Bragg, right? Father and son, Nobel Prize winning tag team combo there. They discovered diffraction, and diffraction can tell you about where atoms are located. And so we knew what the structure was, but we never actually saw it. And then all of a sudden we could visualize it. We can see atoms. You could see the planes, the zigzags, the structures. And it was wild, and, I went to school. I was in school in like the turn of the century, right? Around 2000, I was in school. And back then it was available, but it wasn't great. But still, like, we were looking at atoms, and that was like blowing minds. And I show it to my students now in the year 2022, right? And they're like, yeah, whatever, it's an atom. I'm like, what do you mean it's just an atom? You're looking at atoms. It's amazing. Like, this is such a big deal. And I think that, again, we just take it for granted because it's always been there.
Oh, it's just like that thing where people like will be used to a forest, and if it gets cleared out, their kids will never be used to it. But like, a positive version of that.
Yeah. Another major breakthrough he lists is the giant magnetoresistive effect. And I'm not going to get into how this works because it's complicated, but think about this. In your computers nowadays, we all have awesome solid state drives, which are fantastic because they're fast, they boot so quick, they have all these wonderful things. But back in the day, we had magnetic memory, right? And so to store your zeros and ones that make up your information bytes, you had to have literally like a tiny space, some region of a magnetic material that had a magnetic moment that was pointing up or pointing down. And so if you have these and you've miniaturized them so small, how do you read that magnetic information? Magnetoresistive materials were able to do that. They are so sensitive, so sensitive to tiny magnetic fields that it allowed us to miniaturize data and storage, right? In a way that, still a lot of computers still have some magnetic memory. They're not totally solid state yet, but that's a huge breakthrough. He goes on to list LEDs and lasers. I can't disagree. So much of communication, like I'm talking to you guys today on fiber internet. That's light, right? That's light conducting via laser through little optical fiber cavities, which optical fibers are alone are an amazing materials breakthrough, right? That's
glass,
that's
right?
Huge. What's that?
Really clear glass, right?
Yeah, it's glass. And it's literally, they fire the light with different ratios, and that's how you get your information passages through firing LEDs into little glass tubes, which sounds like totally crazy. And that's currently about the best that we can do in terms of information transfer. It's fantastic.
Yeah, I think I remember in 1991 or so, I was in first grade and we had these little flashlight, little novelty toys that had a bunch of fiber optics at the end, and they just like lit up, and it was just a novelty. It would be like, it was about as cool as Silly Putty or something. You know what I mean?
Oh yeah, like I remember some of those. Like they would change lights as they rotated around.
And I want to say that they were the novelty item before they were used to transmit information. So could you
actually?
imagine? Yeah.
From what I understand, the first fiber optic cables were because someone was doing an experiment where they took molten glass, attached it to a crossbow, and then fired it across their lab.
No way. No way. Now I want to learn about that. Yeah. That would be so cool. Yeah, drawing glass, you can get those super fine. You know what's crazy? They have undersea cables connecting North America and Europe, which are fiber optics. And in the early, like back in the like the Cold War days, when it was like the Russians and the Americans going at it, we would spy on each other by going down to these cables in the ocean that are literally like on the ocean floor. They'd cut it open, the sheath, but you don't want the other people to know you're spying on them. So they would capture what's called the evanescent wave. So inside your fiber optic, the light's bouncing as it passes from one end to the other. And as it bounces along the edge, there's a property called evanescence of waves, where it actually leaves the material ever so slightly. And so as it leaves the glass fiber just a little bit, you can detect its signal as it leaves. So they don't even know, but you've intercepted their message. So one of my early semiconductor professors told us these stories about how they'd spy on each other by intercepting these evanescent waves off of these cables. Totally crazy stuff. Super cool.
And I'm assuming they get like ever so slightly dimmer.
Yep, that's right. That's right. And so there's repeater stations typically. I don't know what they do nowadays. I know back in the day they had repeater stations where they'd take the signal, then they'd retransmit it, and they'd up the intensity again.
Oh yeah, because I know that glass is so clear that like, if it could go 1 mile, you could probably look into the Mariana Trench like just through the glass, and it'd be perfectly clear.
Yeah, so rad.
But anyway, sorry. The rest of your
I won't go on and on, but I mean, it's cool to see some of the things that they listed, like carbon fiber reinforced composites. Again, we just sort of assumed that carbon fiber bikes and tennis rackets and vehicles are just like around, but somebody discovered those, and those were a big deal. Or lithium ion batteries, right? In my lifetime, I saw those go from you never heard of them to everywhere. All right. That's a huge one. Carbon nanotubes, which are still sort of, we keep on waiting for a lot of the killer apps for those. Like, they're really interesting, but they're not transforming our lives in as major of ways you might think, for as much as people have heard of them. Soft lithography, holy cow, metamaterials. Anyways, those are the 10 that he listed. It's a pretty awesome list. I mean, but at the same time, when I read that list, I'm like, but what about Teflon? But what about steel? But what about like superconductors? Like, there's so many things that are left off that list that even coming up with 10 feels impossible.
Goodness.
All right, so now we're going to go kind of ask some questions that are, I mean, some of these are going to be a lot simpler than others, but they're questions that some of them I know I've discussed with you, Gabriel.
Yes.
Some of them I just kind of came up with like in the last week. All right, so I guess the first question I'm going to ask is, what is etching? And lithography, and what is all that? I've read a little into it.
Yeah, so when we started this episode, we were talking about Feynman and his race to go to the bottom. And we said that one of the ways that they did that was using the electron microscope to etch letters into the head of the pin. Nowadays, that's not, you can do, it's called E-beam lithography, electron beam lithography, but it's expensive, right? Because those microscopes, those E-beams, it's under vacuum. You can't do it over big areas. It's not very fast. It's not ideal. What they actually do for miniaturization of circuits is called photolithography. And photolithography means you're using light. And like if you've looked through a microscope, like I've got like a lens, and when you look through the lens, it like shrinks the light or it expands it depending on what type of lens you've got, right? So what if you shrunk that light down so spatially, literally like the footprint of the light gets smaller, right? All of a sudden you can make patterns by shrinking that light down. Like you've got a big macro scale mask where like the channels are like 1 millimeter aside, right? And you can shrink that 1 millimeter down to micron or nanometer scale by just passing it through lenses. That's photolithography. That's how they can do a lot of the miniaturization of microelectronic machinery, integrated circuits. So much of that is all happening via photolithography. Now, to make it happen, you have to have the light has to come down on the surface and interact with the surface. So you asked, what is etching? Well, you want the material to interact with light where maybe it dissolves it away or it doesn't dissolve it, right? There's both positive and negative photoresists. Now, most materials like silicon, if you shine light on it, it's not going to etch it away. You need an acid to do that. So how do they do it? They take the silicon and they put on top of it this polymer material that is cured by light, so that when the light from your mask touches it, it either dissolves it or it sets it up and makes it like a cured hard material. Then you wash away the stuff that isn't cured, and all of a sudden the acid can only attack part of the silicon surface, and it doesn't attack the other part because it's protected by this photoresist. So pretty cool way to do miniaturization and nanostructuring of materials.
And so, like, let's say you have like, can it be done on kind of like arbitrary materials at this point? Like, have we found kind of like the left and right hand? Like, could you etch skin? Like, I know it would go away immediately, but
I'm sure they already do it. I know because like there's a gal in my not in my department, but in my college that does tattoos that are conductive, so they can be antenna. So if you have an internal sensor in your body, say measuring glucose or something, I don't know, but it's underneath the skin, you need to transmit that to somewhere else via an antenna. She actually does tattoos that are conductive that can actually do that. So yeah, can you etch all manner of things? Yeah, I think so. Some things are definitely harder to etch than others, right? Some things require really strong acids like HF. This is one of the problems with working with silicon, right? Silicon, the metal, silicon can be etched pretty easily, but silicon oxide, the oxide that forms and grows on silicon, you typically have to use hydrofluoric acid, which is nasty stuff. So it's not like all things are equally easy to etch, but nowadays, there's really great tools for doing lithography on all manner of surfaces.
I had a little mini question. Do you know what superacids are? I've heard of those.
I've never heard that term. I don't know if that's just like really concentrated or if it's things like aqua regia where you're combining multiple acids together trying to maximize your solubility, but I don't know what they are.
Oh, okay. Aqua regia meaning regal water, right? That a mixture of hydrochloric acid and nitric acid?
Or sulfuric, I can't remember. But yeah, it's a mixture of two acids. It's used pretty regularly just because it dissolves so much.
It dissolves gold, which I think is the reason why the medieval people called it that.
Yeah. I love this part of the podcast.
There's a story. We talked about it in one of our episodes where it was one of the Nobel Prize winners during Nazi Germany. I'm forgetting, during their flight out of the country to preserve the metal that they'd won, they dissolved it, right? So you didn't realize it was gold, and then they were able to reprecipitate it. As the story goes, I'd have to look up the exact case, but yeah, that's as the story goes.
Oh yeah, I've heard of that kind of stuff. I know that some people transporting, let's just say, illegal substances from other countries will sometimes melt it into plastic and make like dog carriers and stuff out of it. And so it's just kind of fascinating how we could do a whole episode, right, on just like materialism and coins and like forgery. I mean, but anyway.
So I just checked. It was actually in 1940. It was George de Hevesy. He dissolved the gold Nobel Prizes of von Laue, a diffraction guy who was one of the early experts in diffraction, and James Franck, who I don't know what he did, but he dissolved him in aqua regia so the Nazis wouldn't get him. How cool, huh? And then they reprecipitated it and recast him.
Wow,
that is cool.
That is amazing. Yeah. So much of this is about burning things and melting stuff down. Now that's kind of where my mind is going. I have a little bit of a curveball question for you here. And this involves fire away, pun intended, right? Okay. Speaking of fire, why are ashes white, gray, or black most of the time?
Gosh, you guys have good questions. So something I learned long ago is not to BS my students. I just tell them I don't know the answer. I will come back next class and tell you about it. So why is ash white? I have no idea. Now that I'm thinking of it, I don't know.
Where would you begin to research the answer to that question?
The internet, man. It's democratized education. I think one of the reasons, if I had to guess, it's that if you took white ash and you condensed it, right? If you packed it all down, I think it would become dark. I think what you're seeing is super, super fine mixture of porosity and the leftover carbon. And that's scattering light white because it's porosity. I know that porosity scatters light in all dimensions. So no one color comes out because it's not like one wavelength of light gets scattered. It all gets scattered. And so it appears white, right? So I think that if you were to compress that down, it actually would be black. But I don't know. It's a good question.
Okay, we will Google search that and we will report back on our next episode. We actually, we'll do that because now I'm curious.
Yeah, you stumped me for sure.
Yeah, no. And actually, part of that question is as I was thinking about metallurgy as well as glass itself and the processes that create glass, I kind of got obsessed a little bit in my mind with lava. And one of the questions I have is, has studying lava and the way it moves and the various melting points and what it does and does not affect, has that focus changed material science much in recent years or at all?
I wouldn't say it's changed in material science, but there is this whole other field of geology and geological engineering and, earth sciences where they study that sort of stuff all the time. And it's fascinating. I work with some of these guys at the University of Utah. We got together because we needed to go to really, really high pressures, like really high pressures. And the people that study the center of the earth, right, the mantle and the core and all these different layers, they go to these high pressures. So I met with this guy named Lowell Miyagi at Utah. And as I was talking to him, as he was talking about the deformation mechanism of parts of the earth under these crazy pressures, he was using the same words that I was using for material science. He was talking about slip systems. He was talking about texturing. He was talking about grains, like all of these things that we use to describe a little dog bone sample that we test in the lab as material scientists. It's the exact same thing happening just at a much larger scale in extreme environments in the field of geology. So we're not as different as I thought anyways. It was sort of a cool moment to be like, oh, we're all doing the same thing. You're just in a different scale. Now, have we taken any of the learning from, say, magma or how the earth moves and improved anything about regular materials? I don't know of any case, but maybe there's an opportunity there for sure.
Yeah, fascinating.
Interesting. I was going to ask you just a follow up to that. What's a slip system?
Yeah. So imagine you've got so go back to our analogy of you're tiling the walls in your kitchen. So there's a pattern. Okay. Now, if you wanted the tiles to slide past one another, imagine they're just rectangular tiles. You could imagine they would slide past one another in some directions. But if you picked some arbitrary angle, those tiles wouldn't slide past each other. Right. Therefore, we have sort of preferred directions in which you can get deformation. Those preferred directions are slip systems.
Cool. Now, I have another peripheral question. I guess this one's less geology related, and this is more about synthetic materials that we've created. And actually, this relates to the field of economics. As I was preparing the outline for this episode, I tried to touch on every single field and see how many fields we can touch on in materials. So with economics, something that interests me is, can you think of any discoveries in material science where a material was made that very, very, very cheap, as in inexpensive, that radically changed things? Like I think of packing peanuts, you know what I mean? Like for packaging, but what ways has material science changed economics?
Tons of ways. Tons of examples of that. From the early days, just think of coke, right? Coke, not like the Coke that you drink, but the coke, the form of carbon that they put in steel way, way back. Like we're talking like 1800s. The people that made all the steel was England. England was like dominating the steel game. It was crazy. They were like making cannons and then turning them, selling them to Spain, who was using them in cannon ships, attacking England. Like it was this whole thing. But back then, to go from iron and make steel, you have to incorporate carbon. And the way that you incorporate carbon is you need some sort of carbon source. And back then they were using trees, right? And they completely deforested England. Like this was a major problem. They deforested their country in like major ways because they were making so much steel and it was so profitable that they were just destroying the landscape. And then all of a sudden they discovered this form of coal called coke, which you could use as a replacement instead of basically burning wood and keeping those ashes. They could just use this form of coal. Absolutely revolutionized things, right? There's been tons of things like that have happened over the years. Polymers displacing different metals. Nowadays, plastics, we use them because they're so much more cost effective than the metal, in addition to having, in some cases, better properties. I think we're on the brink of seeing it happen again. Think of your lithium-ion batteries in your phone and in your drone and in all the devices around us. The current version of lithium-ion batteries are rad. They have crazy high energy density. They can operate at pretty high voltages because that couple gives you 3.6 volts instead of like, 1.5 that your AA batteries have. They're great, but they have cobalt in them, which is a seriously problematic conflict mineral coming out of the Democratic Republic of Congo. Like think little kids in mines, very unsafe conditions. It has a lot of problems.
That country has a horrifying history with
dude,
what's that country? Belgium,
Zimbabwe.
But I was going to say the King Leopold, I believe, killed 20 million people in that area, and it's still ongoing, that violence.
Yeah. So, I mean, the cobalt mines in the DRC, the Democratic Republic of Congo, are a big problem. The lithium we use is also a problem. It's getting crazy expensive. Look up the price of lithium over the last 5 years. It's just like exponential. Like these lithium-ion batteries that are so awesome, we need low cost, economically speaking. That's going to drive the choices we make from a materials perspective. So one of the exciting things about material science is that you're at the forefront, right? You're looking like 10 years into the future because, other engineers, whether you're a mechanical or something or electrical engineer, you guys are making devices that we might see next season. And that's exciting, right? To make the ski that shows up on the mountain next year, that's cool. But what material science does, it unlocks things that are like 10 years in the future. No one's talking about sodium ion batteries right now, but material scientists sure are, because sodium is way cheaper than lithium. And it's not as good as lithium in batteries, but we're trying to find ways to make it work better. So again, this would be a good example of an economic reason why we're trying to transform materials just because lithium is becoming too expensive.
Yeah, it also strikes me just kind of like how material science kind of feeds back into itself continually. But before we go into that, I guess I have one more question, and I think Gabriel has another question. Yep. I've heard about Anthropocene materials that happen because of human, like either waste products or just interaction with the world, like geological rocks that have never been there before. I was wondering if you knew anything about that.
I'm Googling Anthropocene materials right now. Does that just mean human-made materials?
Well, it means that too, but I've heard that there's like rocks and stuff that never used to exist before, but because of pollution have been forming.
Oh, okay. I don't know the answer to that. It would not surprise me.
I mean, it does seem like one. I mean, actually, I think I will keep this in because I've wanted to bring up like some fields. Like, I mean, Feynman is talking about it. Like physics, you ask a question, like someone who's an expert in physics will most of the time be able to tell you an answer of some kind. Biology, less like that. Like he gives the example of who's looking at some kind of cell and they had a rotating part and they're like, how does that happen? And they're like, I don't know. And it seems like material is such a broad field of inquiry. Like, it seems like that would happen frequently.
It does.
Yeah, and Gabriel, you had a question?
Yes. Okay. So my last question was about material science and economics. Now I want to talk about material science and biology and medicine. And I think you may have at least one, if not more, podcast episodes about this. So what can you tell our listeners about how material science has impacted both biology and medicine?
I don't know much about biology, but medicine, like biomedical engineering, it's been profound, absolutely profound. What they can do now with modern biomaterials it's crazy. I had a grant a while back funded by the Department of Defense, right? It was looking at ways to make prosthetics better, right now, if you have like a below the knee amputation, so now you've got your knee, but below that it's been cut off, how do you actually walk on that? What they typically do is they take this sort of sheath made out of like a neoprene, typically is what they use, a neoprene sheath. They put it over your the residual appendage, and then they put the prosthetic sort of just like your prosthetic, your residual appendage sort of rests in a cup there. And so the problem is like these guys in the military, that's what this was funded to do. They're wanting to re-enlist even after they've lost a leg, but they can't pass the agility test because they don't know if they're walking on sand versus grass versus gravel. They don't have that sensation. But if you could just take the implant and drill it right into the bone, then they could feel the difference between those surfaces and they would do better. So that's why we were funded to work on this. Now, the problem is if you drill into your bone and just implant like a prosthetic leg and just drill it right into like, say, your femur. So now it's like hard lined into your body. You get the benefit, but you also get the huge risk of your skin will try and close that wound and it will sort of recede back. Just like if you heard of like gingivitis, like your gums receding back away from your teeth and it exposes the roots of your teeth and then they can fall out and get sick. The same thing can happen, right? The skin is trying to close that wound. And so it's trying to move around the prosthetic device by going down. And if it goes down far enough that it makes contact with the bone, then all of a sudden you have a pathway for infection in the bone, which is not like something you can treat with antibiotics. That's like usually amputation. That's a very bad thing. So what we were working on was we basically said like, well, your teeth have figured this out. We have teeth, which are something that passes through the skin, right? Your gums, they pass through the skin and yet your gums don't recede underneath it, typically in a healthy person. So what is it about a tooth that makes this work when we can't do it with other implants? And we wondered if it happened to be the biomineralization, right? The calcium apatite that makes up your teeth, like I guess it's a fluoroapatite that makes up your teeth. And so we had this crazy idea. We said, what if you took like a metal implant material, like titanium, that's what these implants are made of, but you coated it with the same material that your teeth are made of? Would you see better connectivity of the skin to that so it wouldn't recede? And we did. We saw it on some animal studies that we did with the University of Utah and the Veterans Affairs Hospital there. It was so cool. So that's just one example, but far crazier things have existed with biomaterials.
That's incredible.
And is that related to the whole bone thing that you just talked about? Is that related to the Pinocchio effect?
I don't know what the Pinocchio effect is.
Oh, it's what you do is you have somebody take their hand, put it to their nose, and you do this in a dark room. And what you do is you play the sound that their elbow makes while it's extending. You play that using a special speaker right into their elbow, and they'll feel like their nose is growing.
Oh my gosh. No, I've never heard of that. So I don't know if this is related at all to that, but
yeah, I thought it might be for the sensation, but yeah, it's a crazy world. So one thing I'm going to ask, and I don't know how if this is even a material science question or just a kind of like a buzzword that I heard question, but what is a 4D crystal?
Okay. So that's a very hot topic right now. Time crystals, right? 4D crystals. So normally think 3 dimensions, right? So now we're just talking about X, Y, and Z coordinates, like 3-dimensional space, like the objects all around us, right? So you could imagine a crystal, and a crystal just means something that's periodic, meaning it repeats over and over and over and over. Just like think of like a sheet of graph paper. That little square on your graph paper gets repeated in 2 dimensions on that sheet of paper. And if you had that extending out, now you've got a 3-dimensional crystal, right? Because it's repeating. So what would 4 dimensions look like? So a 4D crystal is one where the atoms are actually moving. They're periodic crystals where they're changing with time, and with time they're becoming periodic, right? So these are really hard to study because you have to do diffraction now as a function of time. So there's experts, but not even that many around the world that are like super experts in this, but it is a hot topic because when you get these time crystals, you can get really cool properties out of them, like really, really low thermal conductivity, for example, but other things as well.
So as a kind of follow-up to that question, so you're saying that, it's not only a lattice in 3D space, but it's a lattice in 4D space, kind of like the wallpaper group has 17 things. Basically, there's 17 different.
That's it. Yeah, you know all about it.
Yeah, and there's like, 216 or 400 ways to do it in 3D?
230 space groups, plus the quasi-crystal, right?
Yeah, and I don't know what the
Sheckman
number...
blew all of our minds and made the quasi-crystal.
And let me look up the number for 4D. Actually, I'll do that later. It's probably in the thousands, though.
It's probably infinite. I don't even, because the thing, it's just like, imagine a crystal structure that shifts from one structure to another one and then back, right? So you could have like endless combinations of that.
Oh, yeah. I'm just thinking.
How many they've actually found, I have no idea.
I'm just thinking of like, just the lattice. The lattices themselves probably can be separated into group. Let me see. Let me check something real quick.
One thing I may ask that's actually not on here is this. I realized that for me, I'm running out of time myself, so I'll be heading out soon. But before I leave, if you were to talk about some interesting fields of study in material science in the U.S. or throughout the world, what are some schools that you can talk about for some of our listeners who might want to learn more about some of the neat areas?
Like universities or topics to study?
Both.
First off, my advice to you, anybody thinking about maybe grad school or programs, ignore the rankings. Rankings are ridiculous. Like, it is an absolute racket. They once did a poll of I forget which department it was, but MIT didn't even have that department. And when they did a ranking, they asked people to rank them. They put MIT in the top 5, and the department didn't exist, right? So there's so much BS, institutional inertia, where there's name value that doesn't actually mean that it's a better program for you. Instead, I would say find somebody who you connect with, who's a great teacher, who's going to be passionate, who's going to get you involved, hopefully get you doing research in the laboratory. That is absolutely the most important thing to do in terms of picking a school. Grad school, same thing. Pick a kick butt advisor. Ignore the rankings. Find somebody who everyone raves about and says, he or she is such a great researcher, such a great advisor. They're going to set you up for success. Look at where their students have gone. I would do that, and I would ignore the rankings. Now, topics, I would say what the things, just like everything, there's trends. 20 years ago when I was in college, it was about nanomaterials, right? Nano everything, nanotubes, nano whatever. And we've sort of seen trends come and go, machine learning, right? That's what I'm doing right now. It is definitely a trend. Materials informatics, right? Applying data science to materials research is very hot right now. Quantum materials are very hot right now. So I would just be aware that they're trends, and that may mean that they're going to not be popular soon, right? Polymers were really big for a while, and then they kind of go away, and some things kind of come back. So those are a couple of the really hot areas right now. But I mean, I would suggest learn the basics, learn the fundamentals. If you want to have your passion project and you do research in one of those hot areas, by all means, go for it. But make sure that you catch the broad fundamentals of everything, so that when you see, maybe you want to switch careers and do something different 10 years down the line, you can do so.
Oh yeah. And by the way, I looked up the number of 4D space groups, 4,783.
Woo!
And then
Crazy.
5D is 222,000 different types of 5D crystals. So I don't know what those would be.
Absolutely nuts.
But yeah, let's see.
There's some fascinating questions that you put here under exotic materials. I just read ahead them now for the first time.
How about electricity and knitting or weaving?
Like wearables, textiles that have conductive properties.
Well, I was thinking either that, or I was also thinking what if you took a wire and you crocheted it into a disc that keeps expanding into a hyperbola, and kind of put different sensors here and there. I've always kind of wondered about that, but I'm not sure if anybody does research on that.
I mean, there is research in textiles. There is a lot of research in textiles. Now, this specific mathematical thing that you're describing, I haven't seen anybody doing stuff like that. It wouldn't surprise me if it's out there. It's just far from what I do, though.
Oh, okay, but they do lots of textiles.
But yeah, North Carolina has a huge textile institute, right? And they make, and it's a good thing they do, but they teach us how to fabricate better polyethylene and polystyrene, all these different things like textiles that you can turn into clothing and fibers and rugs, and there's definitely expertise in that. It's more niche though, right? Like I said, there's a couple schools that do it as opposed to everybody.
Yeah.
Like Akron, University of Akron, they do it. North Carolina does it. There's a couple.
So I'm going to just ask you this then. What's the freakiest material you're aware of?
The freakiest material? Oh, geez, I was unprepared for that.
Or name a couple if you want.
I'll say that topological insulators are pretty wild. They are in this quantum material phase that everyone is super excited about. This idea that you can make a material that only conducts along the surface and not through the bulk, because the surface states have different, the band that makes up whether or not something conducts, the bonding essentially happening at the surface is different. That's so cool. That's really, really cool. So I think that's got to be up there. Yeah, that one definitely comes to mind.
And the final question I have is, how does materialism feed back into itself through I'm noticing tool usage is one thing where you need certain tools. For example, if you don't have a really sharp knife, if you don't have a pickaxe, you can't mine, but if you don't mine, you can't, get the next thing.
Like Minecraft, right?
Yeah, exactly.
Totally.
Yeah,
it's happening all the time. Yeah, like take like microscopes. Like you want a microscope that can be higher resolution. Well, to do that, you need better magnetic materials to confine that electron beam to a smaller area. You need more accurate sensors to pick up the tiny now signal coming off the atoms. Like it's just constantly building on itself. Like squid magnetometers, right? That takes advantage of superconductors. Before we had superconductors, we couldn't have squid magnetometers that measure the magnetic moment of these really, really sensitive materials. Like it's constantly building on itself. That's just in sort of measurement. But in terms of devices, the same thing. Like at components, you need materials that have a certain strength to make some sort of overall device or a certain density. And before that exists, it doesn't really, you can't do it. And then all of a sudden that material exists and it unlocks new components and devices that can be manufactured. So it's a field that's constantly reinventing itself.
Nice. Yeah. And you mentioned you need for the stronger magnets, you need superconductors. I imagine you need a lot of stuff for the superconductors, and it goes probably all the way back to the first bacteria. The whole world around us is made from matter, and it's the arrangement of that matter that allows us to derive use from it. We've explored everything from transparent conductors to time crystals, and since we're talking about a science that has only been around in a unique form for less than a century, we have a lot of cool stuff to look forward to. I'm Sofía.
And I'm Gabriel.
And this has been Breaking Math. With us, we had on Taylor from the Materialism podcast. You want to plug that? When's it update, etc.?
If you haven't heard of the Materialism podcast, I think you got to check it out. We talk about the past, present, and future of material science. It's super duper approachable. We try and explain simple concepts, and we have sort of rotating themes talking about the history of known materials, the discovery of new materials, crazy ways that people can characterize or measure materials or process them in different ways. We think it's a pretty fun series of episodes, so I hope you check it out. Cool.
And any good episode for someone to start with?
For this math audience, let me think. Well, let me just say, one of my favorite episodes is on my own research, materials informatics. But one that we get great feedback from is on SPS. It stands for spark plasma sintering. It's a processing technique that has sort of revolutionized materials. People seem to love that one, so maybe that's a great place to start. Or, if all else fails, go to our very first one. It has 10 times more listens than anybody else, and that's the history of steel. Steel is one of these materials that's just like tied with human history in amazing ways.
Oh, yeah, right. Yeah. Cool. So, that is the end of the podcast.
Grand Canyon University's RN to BSN online degree program makes earning your bachelor's in nursing possible. Balance online coursework with local in-person clinicals to position yourself for potential leadership opportunities in the time you have from wherever you are, leaving room for what matters. Achieve your goals with your personalized plan and team behind you. Find your purpose at Grand Canyon University. Visit gcu.edu.